Scientist constructs a galvanic cell as shown in the diagram. The cell operates, the zinc electrode increases in mass, and the aluminum electrode decreases in mass. A data table with the standard reduction potentials is shown down below. So we're given our voltage, which is nice. And first it says, write out the half reaction for the oxidation that occurs at the anode. So here we have a higher value on our standard reduction chart. So this is actually going to be what is being reduced. So this is our cathode. This is what's being oxidized. And so this is our anode. So it just wants the half reaction. So all I think it wants us to do is to just flip this equation. So we're going to have aluminum as a solid, Al, 3 plus, that's aqueous, and 3 electrons. Interesting entry question. Pretty straightforward here. It says write the balanced net ionic equation for the overall reaction. So we need to make sure that we combine these two reactions. Remember that when you combine half reactions, you need to make sure that the moles of electrons cancel in them. So we need to take this equation, multiply by 3. This equation, multiply by 2. Remember that this equation is also the one that is flipped. So when we write this out, we're going to have 3 Zn, 2 plus, that's aqueous, plus 2 aluminum, that's solid, arrow, 2 aluminum, 3 plus, that's aqueous, and 3 solid zincs. Okay, so there's the full overall reaction here. It says initially, each electrode has a mass of 50 grams. When the cell is allowed to run for a period of time and is then stopped, which electrode's mass changed the most? And justify with the calculation. Okay, I've not seen anything quite like this before, so this is an interesting question. Okay. I mean, I already know the answer by looking at it, but it says justify it with a calculation. I'm going to lose 2 moles of aluminum and gain 3 moles of zinc. Molar mass of aluminum is 26.98, whereas zinc's is, give me a second, 65.38. So I already know based off of this information that I'm losing an extra mole of zinc and its molar mass is larger. So I know zinc is the right answer here, is going to be what changes the most, but calculating it, I think I could do this. Let's say we start off with losing 5 grams of aluminum, right? We lose aluminum in this process, correct? Yeah, aluminum decreases in mass. So if we lose 5 grams of aluminum, I bet I can do a molar conversion here. So 26.98 grams to 1 mole of aluminum. Let's use the mole ratio here. So 2 moles of aluminum to 3 moles of zinc. And then 1 mole of zinc, 65.38 grams. So I bet if I do it this way, I can show that for every 5 grams of aluminum that react, I produce so many grams of zinc. And as a result, I can prove that the zincs will change more. So if I calculate this, so 5 divided by 26.98 times 3 divided by 2 times 65.38, 18 grams of zinc. So I think that proves it with the calculation. If you have another way of doing it, let me know. I'm curious. But for every 5 grams of aluminum that react, 18 grams of zinc is produced. So I think that tells me that zinc changes more. And yeah, I think that answers the question. At least I hope it answers the question. I'm sure there's a different way to do it. It's just kind of the first thing that popped into my head. I have not seen anything like that before. So quite interesting. All right, so we're given a bunch of other half reactions here. Let's see what it says. It says the standard zinc aluminum cell has a voltage of 0.9. The scientist needs a galvanic cell that produces a greater voltage. The scientist has access to the chemical systems in the table. And I want to create, using zinc, so we're using this, what is the maximum voltage that can be generated under standard conditions? So I'm going to go ahead and eliminate a couple of these. Basically, it's either going to be the one at the top or the one at the bottom. That's kind of how this always works here. So if I use Be, we keep negative 0.76, but this beryllium gets flipped to 1.85. So if I use beryllium here, I end up with 1.09 volts. If I use gold, we keep the 1.50, but we flip the zinc. So 0.76. So 1.5 plus 0.76 gives me a voltage of 2.26 volts. So our winner here is gold, because that will produce a voltage of 2.26 volts. Yeah, all right. Pretty tame voltaic cell question. Don't mind that by any means. So really, really well done. Again, good entry point here, some good questions. I think this C part is going to throw some people for a loop because I don't know. It's not something that I explicitly cover, so I'm curious to see what my students come up with. But again, we'll just have to kind of wait and see how this turns out. So that's the end of part 6. Let's move on to the last and final question. Always a sad time when we get to the final question of the year.